Hello, and welcome back. I'm so glad you're here with me tonight. If you're returning from our ocean journey, welcome home. If this is your first time, welcome to a place of rest and wonder. Tonight, we're leaving Earth behind. We're going to drift through the solar system and beyond, exploring the planets that circle our sun and the countless worlds that orbit distant stars. There's something deeply humbling about contemplating the planets, isn't there? These massive spheres of rock and gas spinning through the void, each one a world unto itself. Some are hellishly hot, others frozen beyond imagination. Some have storms that have raged for centuries, others are so still they seem almost dead. And yet each one has its own story, its own strange beauty. Over the next few hours, we're going to explore 100 facts about planets. But this isn't a test. There's nothing to memorize, nothing to prove. Just let these stories wash over you like starlight. If you drift off before we reach the end, that's exactly what should happen. That's why we're here, so settle in. Get as comfortable as you possibly can. Adjust your pillow one last time. Pull your blanket up to just the right spot. And let's begin our journey through the planets, starting right here at home, then spiraling outward into the cosmic dark. Our Earth is the only planet in the universe that we know for certain harbors life. Think about that for a moment. In all the vastness of space across all the billions of galaxies, each containing billions of stars, each potentially surrounded by planets, Earth is the only place where we can point and say with absolute certainty that life exists. That makes our planet unimaginably precious, but it also raises a profound question. Are we truly alone, or have we simply not looked far enough, not listened carefully enough? Earth sits in what astronomers call the habitable zone, that perfect distance from the sun where water can exist as a liquid on the surface. Too close and water boils away. Too far and it freezes solid. But Earth sits right in that Goldilocks region, not too hot, not too cold, but just right. Our planet is about 93 million miles from the sun, and that distance makes all the difference. If Earth were just 5% closer to the sun, we might have suffered the same fate as Venus, with a runaway greenhouse effect that boiled away the oceans and created a toxic, scorching hellscape. If we were 15% farther away, we might have frozen like Mars, our atmosphere gradually stripped away by solar wind, our water locked in polar ice caps and underground reservoirs. Instead, we orbit at precisely the right distance for liquid oceans, for an atmosphere that's neither too thin nor too thick, for temperatures that allow complex chemistry, and eventually, life at Earth is the largest of the rocky planets in our solar system. It has a diameter of about 7,900 miles, and it's composed primarily of iron, oxygen, silicon, and magnesium. But what makes Earth truly unique isn't its size or composition. It's the fact that our planet is geologically alive. The surface of Earth is broken into massive tectonic plates that drift slowly across the mantle beneath, colliding and separating, building mountains and opening ocean basins. This plate tectonics is crucial for maintaining life. It recycles carbon, keeping our atmosphere stable over geological timescales. It creates diverse landscapes and climates, and it might be quite rare. Of all the rocky planets and moons we've studied in our solar system, Earth is the only one with plate tectonics still actively reshaping its surface. Venus might have had it once but lost it. Mars might never have had it at all. This constant recycling of Earth's crust might be one of the key ingredients for long-term habitability. And if that's true, then habitable planets might be even rarer than we thought. The Earth has one moon, which we simply call the Moon, and it's unusual in several ways. First, it's remarkably large compared to Earth. Most moons in the solar system are tiny compared to their parent planets, but our moon is about 1/4 the diameter of Earth. This makes the Earth-Moon system almost a double planet, rather than a planet and its satellite. The leading theory for how the moon formed is both violent and fascinating. About 4.5 billion years ago, when the solar system was still young and chaotic, a Mars-sized object that scientists have named Theia crashed into the proto-Earth. The collision was catastrophic, vaporizing much of both bodies. The debris from this impact was thrown into orbit around Earth, and over time, This debris coalesced into the moon. This means the moon is literally made of pieces of Earth and pieces of whatever Theia was, blended together in the heat of that ancient collision. The moon has been gradually drifting away from Earth ever since it formed, moving about 1.5 inches farther away each year. Billions of years ago, the moon was much closer, looming enormous in the sky, and its gravitational pull created massive tides that may have helped kickstart the chemistry that led to life. Today, the moon is far enough away that total solar eclipses are only possible because of an extraordinary cosmic coincidence. The moon is about 400 times smaller than the sun, but it's also about 400 times closer, so they appear almost exactly the same size in our sky. Earth spins on its axis once every 24 hours, giving us our day and night cycle, but that rotation is gradually slowing down, again because of the moon's gravitational pull. The tidal forces between Earth and moon create friction that acts like a brake on Earth's rotation. About 600 million years ago, a day was only about 22 hours long. 100 million years from now, a day might be 25 hours long. This is happening incredibly slowly, but it's happening. Eventually, billions of years in the future, if the sun doesn't swallow both Earth and moon first, Earth's rotation will slow enough that the same side of Earth will always face the moon, just as the same side of the moon always faces Earth now. At that point, the moon will appear to hang motionless in the sky from one hemisphere of Earth, while being permanently invisible from the other hemisphere. Mercury is the closest planet to the sun, orbiting at an average distance of about 36 million miles. It's a small world, only slightly larger than our moon, with a diameter of just over 3,000 miles. Mercury takes only 88 Earth days to complete one orbit around the sun, making its year shorter than the seasons on Earth. But here's something strange. While Mercury races around the sun, it rotates incredibly slowly on its axis. It takes 59 Earth days for Mercury to complete one rotation. This creates a bizarre situation. Because of the combination of its orbit and rotation, if you were standing on Mercury's surface, you'd experience a day that lasts 176 Earth days from sunrise to sunrise. Imagine a day that lasts almost 6 Earth months. You'd watch the sun creep incredibly slowly across the sky, taking months to rise, months to cross overhead, months to set. The temperature variations on Mercury are the most extreme in the solar system. During its long day when the sun is overhead, surface temperatures can reach 800 degrees Fahrenheit, hot enough to melt lead. But Mercury has virtually no atmosphere to trap heat, so during the long night, temperatures plummet to minus 290 degrees Fahrenheit. That's a temperature swing of over 1,000 degrees. No other planet experiences anything close to this. Standing on the surface of Mercury would require protection not just from radiation and heat, but from these incredible temperature extremes. You'd slowly roast during the day and freeze solid during the night. Despite being the closest planet to the sun, Mercury isn't the hottest planet in the solar system. That title belongs to Venus, and there's a fascinating reason why. Mercury's lack of atmosphere means it can't retain heat. As soon as the sun sets, the heat radiates back into space. Venus, on the other hand, has an incredibly thick atmosphere, mostly carbon dioxide, which traps heat in a runaway greenhouse effect. So even though Venus is nearly twice as far from the sun as Mercury, it's actually hotter. This teaches us something important about planetary science. Distance from the sun matters, but atmosphere matters even more. Mercury has a surface that's heavily cratered, looking somewhat like our moon. These craters are the scars of billions of years of impacts from asteroids and comets. One of the largest is the Caloris Basin, a massive impact crater about 960 miles across, created by an asteroid collision so powerful it sent shockwaves through the entire planet. On the opposite side of Mercury from the Caloris Basin, the landscape is strangely jumbled and chaotic, and scientists believe this weird terrain was created by the focused seismic waves from that same impact, converging on the far side of the planet with enough force to fracture and disrupt the surface. An impact on one side of the planet literally reshaped the other side. Mercury has a magnetic field which is surprising for such a small planet. Most planetary magnetic fields are generated by liquid iron cores that move and create dynamo effects. Earth has a strong magnetic field for this reason, but Mercury is so small that scientists expected its core to have solidified billions of years ago, shutting down any magnetic field. Yet Mercury still has a magnetic field, albeit a weak one, about 1% the strength of Earth's. This suggests that Mercury's core is at least partially liquid, which raises questions about the planet's internal structure and thermal evolution. For such a small world so close to the Sun, Mercury still has mysteries we haven't fully solved. There are permanently shadowed craters at Mercury's poles that never receive sunlight. These craters are so deep and at such high latitudes that the Sun never rises high enough to illuminate their floors. Scientists have detected what appears to be water ice in these permanently shadowed regions. On a planet where daytime temperatures can melt lead, there are places that are perpetually frozen, preserving ice that might be billions of years old. This ice probably came from comet impacts long ago, and it survived because these crater floors are among the coldest places in the inner solar system. Shielded from the Sun by the crater walls, and I'm unable to warm up. We're 10 facts in, and I hope you're starting to relax. Let your mind wander through these worlds. There's no rush. The planets have been spinning for billions of years. They'll wait for us. Venus is often called Earth's sister planet because it's similar in size, mass, and composition. Venus has a diameter of about 7,500 miles compared to Earth's 7,900. It orbits the Sun at about 67 million miles between Mercury and Earth. For a long time, people imagined Venus might be like Earth, perhaps with oceans and life, hidden beneath its permanent cloud cover. Early science fiction often portrayed Venus as a tropical, swampy world. But when we finally sent probes to Venus in the 1960s and 70s, we discovered something very different. Venus is hell. The surface temperature on Venus is about 900 degrees Fahrenheit, hot enough to melt lead, hot enough to make certain metals glow. This is hotter than Mercury, even though Venus is almost twice as far from the Sun. The reason is Venus's atmosphere. It's incredibly thick, with a surface pressure 90 times greater than Earth's, equivalent to being 3,000 feet underwater in Earth's oceans. And it's composed almost entirely of carbon dioxide, with clouds of sulfuric acid. This creates an extreme greenhouse effect. Sunlight penetrates the atmosphere, heats the surface, and then the heat is trapped by all that carbon dioxide, unable to escape back into space. The temperature just keeps building until it reaches an equilibrium at those hellish levels. Venus rotates incredibly slowly and in the opposite direction from most planets. While Earth and most other planets rotate counterclockwise when viewed from above the North Pole, Venus rotates clockwise. Scientists call this retrograde rotation. And it's slow. Venus takes 243 Earth days to complete one rotation on its axis, but it only takes 225 Earth days to orbit the Sun. This means that on Venus, a day is longer than a year. If you were standing on the surface of Venus, you'd see the Sun rise in the west and set in the east, very slowly, taking months to cross the sky. And because of the thick cloud cover, you wouldn't see the Sun directly anyway. It would just be a diffuse glow moving across the perpetual twilight of the Venusian sky. The clouds on Venus are made of sulfuric acid droplets. Sulfuric acid is corrosive enough to eat through metal and burn human skin on contact. These clouds form a permanent layer that completely obscures the surface from view. Early astronomers looking at Venus through telescopes saw a featureless white globe. They could see the phases of Venus as it orbited the Sun, sometimes appearing as a crescent, sometimes nearly full, but they could never see any surface features. It wasn't until we developed radar that could penetrate the clouds that we could map the surface of Venus, and what we found was a world covered in volcanic features. There are vast lava plains, enormous volcanoes, and strange geological features called coronae, circular structures hundreds of miles across, formed by rising plumes of hot rock from deep within the planet. Venus might have had oceans once, billions of years ago when the Sun was dimmer and cooler. But as the Sun brightened over time, Venus reached a tipping point. The oceans began to evaporate, putting more water vapor into the atmosphere. Water vapor is itself a greenhouse gas, so this trapped more heat, which caused more evaporation, which trapped more heat. This is called a runaway greenhouse effect. Eventually, all the water was in the atmosphere. Then, because Venus lacks a magnetic field, solar radiation broke down the water molecules in the upper atmosphere. The hydrogen, being light, escaped into space. The oxygen reacted with rocks on the surface. Over hundreds of millions of years, Venus lost all its water this way. Today, Venus is bone dry. If Earth were just slightly closer to the Sun, we might have suffered the same fate. Venus is a cautionary tale about what can happen when greenhouse effects spiral out of control. Despite its hellish conditions, Venus might have life in its clouds. This sounds absurd at first. The surface is hot enough to melt lead, and the clouds are made of sulfuric acid. But high in Venus's atmosphere, about 30 miles above the surface, the temperature and pressure are actually quite Earth-like. It's still not pleasant. You'd need to breathe oxygen you brought with you, and you'd need protection from the sulfuric acid. But the temperature at that altitude is around 85 degrees Fahrenheit, and the pressure is about the same as Earth's surface. There are bacteria on Earth that can live in acidic conditions, and some scientists have speculated that microbes might exist in Venus's clouds, floating in the relatively temperate zone, reproducing and evolving, never touching the hellish surface below. In 2020, scientists announced the detection of phosphine gas in Venus's atmosphere, and phosphine is associated with life on Earth. The discovery was controversial, and subsequent observations have been ambiguous, but it raised the tantalizing possibility that our hellish neighbor might not be completely lifeless after all. Soviet Venera probes managed to land on Venus's surface in the 1970s and 80s, a remarkable achievement considering the conditions. These probes were built like tanks, with thick pressure hulls and sophisticated cooling systems. Even so, most of them only survived for an hour or two before being destroyed by the heat and pressure. But in that brief time, they sent back the only photographs we have of Venus's surface. The images show a rocky, barren landscape under an orange sky, lit by the diffuse sunlight filtering through the clouds, flat rocks scattered across the ground stretching to the horizon. It looks alien and dead, and yet strangely beautiful in its desolation. These are some of the most otherworldly photographs in the history of space exploration, images from the surface of hell. Mars has captivated human imagination more than any other planet. It's visible to the naked eye, glowing rust red in the night sky, and even through small telescopes. You can see features on its surface, polar ice caps, and dark regions that early astronomers thought might be seas. In the late 1800s, Italian astronomer Giovanni Schiaparelli observed what he called canali on Mars, an Italian word meaning channels. But when his observations were translated into English, the word became canals, which implies artificial construction. American astronomer Percival Lowell became convinced that these canals were built by an ancient Martian civilization trying to transport water from the polar caps to the arid equatorial regions. Lowell spent decades mapping these canals and speculating about the Martians who built them. Of course, when better telescopes and eventually spacecraft gave us clear views of Mars, we discovered there are no canals. What Lowell saw were optical illusions, tricks of the eye and atmosphere. But the idea of Martians had captured the public imagination, and in a way, it still has. Mars is about half the diameter of Earth, with about 1/10 of Earth's mass. It's a small, cold world, orbiting the Sun at an average distance of about 142 million miles, about 1.5 times Earth's distance from the Sun. Mars takes 687 Earth days to orbit the Sun, so a Martian year is almost twice as long as an Earth year. But a Martian day is remarkably similar to an Earth day. Mars rotates once every 24 hours and 37 minutes. This similarity is one reason why Mars is often considered the most likely target for future human colonization. Living on Mars would require adapting to a different year length, but the day-night cycle would feel familiar. The surface of Mars is covered in iron oxide, rust, which gives the planet its reddish color. This rust is evidence of a complex chemical history. Iron doesn't rust without oxygen, which means that at some point there was oxygen available in Mars's environment. Today, Mars's atmosphere is incredibly thin, less than 1% the density of Earth's atmosphere, and it's mostly carbon dioxide with just traces of nitrogen and argon. There's virtually no oxygen, and the atmospheric pressure is so low that liquid water can't exist on the surface. Any water would either freeze or evaporate immediately. But the presence of all that rust, along with other geological evidence, suggests that Mars once had a thicker atmosphere and liquid water on its surface. Mars has the largest volcano in the solar system, Olympus Mons. This shield volcano is about 374 miles across at its base and rises about 13.5 miles above the surrounding plains. That's nearly 2.5 times the height of Mount Everest. Olympus Mons is so large that if you were standing on its slopes, the summit would be beyond the horizon, and the base would be beyond the horizon in the other direction. You wouldn't be able to see the whole volcano at once. You'd just see a gentle slope extending in both directions, farther than you could see. The caldera at the summit is about 50 miles wide and could easily swallow a small city. Olympus Mons is extinct now, or at least dormant. It probably hasn't erupted in millions of years. But when it was active, it must have been an awe-inspiring sight. A mountain taller than any on Earth, spewing lava and ash into the thin Martian air. We're 20 facts into our journey. Let yourself sink deeper into relaxation. These planets have been orbiting for eons, and they'll still be there tomorrow. Right now, just breathe and listen. Mars has 2 small moons, Phobos and Deimos, Greek names meaning fear and dread, named after the horses that pulled the chariot of Ares, the Greek god of war. Mars is the Roman equivalent of Ares, so the naming is thematically appropriate. But Phobos and Deimos don't look like moons. They look like captured asteroids, lumpy and irregular, covered in craters. Phobos is only about 14 miles across at its widest point, and Deimos is even smaller at about 8 miles across. These moons are so small and so close to Mars that from the Martian surface, they'd look quite strange in the sky. Phobos orbits Mars about 3 times per day, so you'd see it rise in the west and set in the east several times per day, moving visibly across the sky. Deimos orbits more slowly and would appear as a bright star that takes several days to cross the sky. Neither moon is large enough to appear as a disk to the naked eye from Mars's surface. They'd just be very bright points of light. Phobos is gradually spiraling inward toward Mars. It's losing orbital energy through tidal interactions with Mars, and in about 50 million years it will either crash into Mars's surface or, more likely, be torn apart by tidal forces, creating a ring system around Mars, so far in the future that no human will ever see it. But Mars will temporarily become a ringed planet, with debris from the shattered Phobos forming a band across the Martian sky. The evidence for past water on Mars is everywhere. There are vast networks of valleys that look like dried-up riverbeds. There are minerals that only form in the presence of liquid water. There are what appear to be ancient ocean basins. The Mars rovers have found rounded pebbles, the kind that form when water tumbles rocks against each other. All of this points to a Mars that was once much warmer and wetter, possibly billions of years ago, when it had a thicker atmosphere that could trap heat and maintain liquid water on the surface. What happened to that water? Some of it is frozen in the polar ice caps and underground ice deposits. Some of it was broken down into hydrogen and oxygen by solar radiation, and the hydrogen escaped into space. Mars lost its thick atmosphere gradually because, unlike Earth, Mars doesn't have a strong magnetic field to protect its atmosphere from being stripped away by the solar wind. Over hundreds of millions of years, Mars's atmosphere was eroded away. The planet grew colder, the water froze or evaporated, and Mars became the cold, dry world we see today. The possibility of life on Mars has fascinated scientists for over a century. We know Mars once had conditions that might have been suitable for life: liquid water, a thicker atmosphere, possibly a warmer climate. Did life arise there? If it did, Does any of it survive today, perhaps as hardy microbes, living underground where there's still liquid water and protection from radiation? In 1996, scientists announced they had found possible evidence of fossilized bacteria in a Martian meteorite that had fallen to Earth. The meteorite, designated ALH 84001, contained structures that looked like tiny fossilized microbes and chemical signatures associated with biological activity. The announcement was huge news, discussed at the highest levels of government and science, but subsequent research cast doubt on the findings. The structures might be mineral formations that just happen to look biological. The chemical signatures might have come from contamination on Earth. Today, most scientists don't believe ALH 84001 contains evidence of Martian life, but the debate isn't completely settled. And even if that particular meteorite doesn't contain fossils, it doesn't mean Mars was never home to life. We've barely scratched the surface of Mars, quite literally. We've explored tiny fractions of one planet. There is so much more to search. Current Mars rovers like Perseverance are specifically designed to look for signs of past life. Perseverance is exploring Jezero Crater, which appears to have once been a lake. The rover is collecting rock samples that will, hopefully, be returned to Earth by a future mission in the 2030s. These samples will be analyzed in laboratories with equipment far more sophisticated than anything we can send to Mars. If there's fossilized evidence of past life in those rocks, we'll find it. And if we do find evidence that life arose independently on Mars, it would be one of the most profound discoveries in human history. It would tell us that life isn't a unique accident that happened only on Earth, but rather a natural consequence of the right chemical and physical conditions. It would suggest that the universe might be full of life, that we're not alone, that life is as fundamental a part of the cosmos as stars and galaxies. Jupiter is the giant of our solar system, the largest planet by far. It has a diameter of about 89,000 miles, more than 11 times Earth's diameter. You could fit over 1,300 Earths inside Jupiter's volume. But Jupiter isn't made of rock and metal like Earth. It's a gas giant, composed mostly of hydrogen and helium, the same elements that make up the Sun. In fact, Jupiter is sometimes called a failed star because it's made of star stuff, but didn't quite get massive enough to ignite nuclear fusion in its core. If Jupiter were about 80 times more massive, it would become a star, fusing hydrogen into helium and glowing with its own light. But at its current mass, it's just a planet, the largest planet, but still just reflecting the Sun's light rather than generating its own. Jupiter's most famous feature is the Great Red Spot, a massive storm that's been raging for at least 300 years, possibly much longer. We've been observing it since the 1600s when telescopes became powerful enough to see it. The Great Red Spot is enormous, about 10,000 miles across, large enough to swallow Earth whole. It's an anticyclonic storm, meaning it rotates counterclockwise in Jupiter's southern hemisphere, opposite to the direction a hurricane would rotate in Earth's southern hemisphere. The storm's reddish color comes from complex organic molecules created by sunlight acting on Jupiter's atmospheric chemicals, though the exact chemistry isn't fully understood. What we do know is that this storm has been going for centuries without showing any signs of stopping. On Earth, hurricanes lose energy when they pass over land or cold water. But Jupiter has no land and no ocean. It's just atmosphere all the way down, until eventually the gas becomes so dense and hot that it transitions into liquid hydrogen. Without anything to disrupt it, the Great Red Spot just keeps spinning, powered by Jupiter's internal heat and the complex dynamics of the planet's atmosphere. Recently, scientists have noticed that the Great Red Spot is shrinking. Observations from the 1800s suggest it was much larger than, perhaps twice, its current size. It's been steadily shrinking for over a century, and we don't fully understand why. At the current rate, it might disappear entirely within a few decades, though it might also stabilize at a smaller size. The thought that this iconic feature of our solar system, a storm that's raged for centuries, might disappear within our lifetimes is both sad and fascinating. It's a reminder that even on Jupiter, Even with storms that last for centuries, nothing lasts forever. Change happens everywhere, on all scales, from microbes to planets to storms that could swallow worlds. Jupiter has at least 95 known moons, and we're probably still discovering more. The four largest, Io, Europa, Ganymede, and Callisto, were discovered by Galileo in 1610 when he pointed one of the first astronomical telescopes at Jupiter. These Galilean moons, as they're called, are worlds in their own right. Ganymede is the largest moon in the solar system, bigger than the planet Mercury. It has its own magnetic field, the only moon that does. Callisto is heavily cratered, one of the oldest surfaces in the solar system, virtually unchanged for billions of years. Io is the most volcanically active body in the solar system, with hundreds of active volcanoes covering its surface. And Europa, well, Europa might be one of the most important objects in the solar system. Europa is covered in a layer of ice, but beneath that ice, there's almost certainly a global ocean of liquid water. We know this from several lines of evidence. Europa's surface shows evidence of ice flowing and fracturing in patterns consistent with a liquid layer underneath. Europa's magnetic field fluctuates in ways that suggest a conducting fluid beneath the ice, and salt water would be conducting. And calculations based on tidal heating, the gravitational squeeze Europa experiences as it orbits Jupiter, suggest there should be enough energy to keep water liquid beneath the ice. This ocean might be deeper than all of Earth's oceans combined, containing twice as much water as Earth, despite Europa being smaller than our moon. And where there's liquid water and energy, there's potential for life. Europa's ice shell is probably tens of miles thick in most places, but there might be thinner areas, and there might be places where the ocean water occasionally breaks through to the surface. The surface of Europa is crisscrossed with reddish-brown cracks and ridges, giving it a distinctive appearance that's been compared to a cracked egg or a marble. These cracks are probably caused by the stresses of tidal heating and the ice shell moving over the liquid ocean beneath. The reddish color might be salts from the ocean or organic molecules created by radiation. If there's life in Europa's ocean, it would be living in complete darkness, never seeing the sun, never even knowing there is a sun. Any life there would be based on chemical energy, perhaps around hydrothermal vents on Europa's ocean floor, similar to the ecosystems around hydrothermal vents in Earth's deep oceans. NASA is planning a mission called Europa Clipper that will orbit Jupiter and make multiple close flybys of Europa, studying the ice shell, measuring its thickness, and looking for places where ocean water might be venting into space through cracks in the ice. If we're lucky, the spacecraft might be able to sample that water and analyze it for signs of life without even having to land. 30 facts down, and we're still just scratching the surface of our own solar system. There's so much to explore, so many worlds, each with its own story. Rest your eyes if you'd like. Let these words be like a gentle tide, carrying you towards sleep. Jupiter's magnetic field is the strongest of any planet in the solar system, about 20,000 times stronger than Earth's. This magnetic field creates a magnetosphere around Jupiter that extends for millions of miles into space. The magnetosphere traps charged particles from the solar wind and from volcanic eruptions on Io, creating intense radiation belts around the planet. These radiation belts are so powerful that they're a major hazard for spacecraft. The electronics on any probe approaching Jupiter have to be specially hardened against radiation, and even then, the intense radiation gradually degrades them. If a human were in orbit around Jupiter without shielding, the radiation would be lethal within hours or days. This is one of the major challenges for any future mission to explore Jupiter's moons. We need to develop better radiation shielding or plan very short missions to minimize exposure. Jupiter acts as a cosmic vacuum cleaner for the inner solar system. Its enormous gravity pulls in comets and asteroids that might otherwise hit the inner planets. This became dramatically clear in 1994 when comet Shoemaker-Levy 9 broke apart and crashed into Jupiter. Astronomers around the world watched as fragment after fragment plunged into Jupiter's atmosphere, creating enormous dark scars that lasted for months. Some of these impacts released energy equivalent to millions of nuclear bombs. If a comet like that had hit Earth, it would have been an extinction-level event. But Jupiter absorbed it without a scratch, or at least without any permanent damage. This protection that Jupiter provides might be one of the reasons life was able to evolve on Earth. Without Jupiter, Earth might have been hit by many more asteroids and comets over its history, potentially preventing complex life from ever developing. Jupiter rotates faster than any other planet in the solar system. Despite its enormous size, it completes one rotation in just under 10 hours. This rapid rotation causes Jupiter to bulge at its equator. Jupiter is noticeably oblate, meaning it's wider at the equator than at the poles. The equatorial diameter is about 7,000 miles larger than the polar diameter. This rapid rotation also drives Jupiter's complex atmospheric dynamics. The atmosphere is divided into bands that run parallel to the equator, alternating between light zones and dark belts. These bands represent rising and sinking air masses, with the light zones being areas where gas is rising and forming ammonia ice clouds, and the dark belts being regions where gas is sinking. The boundaries between these bands are regions of intense winds, with speeds of up to 400 miles per hour. Jupiter's atmosphere is a constantly churning system of storms and jet streams, far more dynamic and violent than anything on Earth. If you could somehow sink down through Jupiter's atmosphere, past the clouds and bands, past the Great Red Spot, you'd find that the atmosphere gradually gets denser and hotter as the pressure increases. Eventually, thousands of miles down, the hydrogen gas would become so compressed by the immense pressure that it would transition into liquid hydrogen. Go deeper still, and the pressure becomes so extreme that the hydrogen transitions again, this time into liquid metallic hydrogen, a strange state of matter that doesn't exist naturally on Earth. In this form, hydrogen conducts electricity like a metal. It's this layer of metallic hydrogen, flowing and moving due to Jupiter's rapid rotation, that generates Jupiter's powerful magnetic field. At the very center of Jupiter, about 40,000 miles below the cloud tops, there might be a rocky core larger than Earth, but we're not certain. The core might be dissolved into the surrounding metallic hydrogen. Jupiter is so strange and so extreme that even with all our observations and models, there's still much about its interior structure that we don't fully understand. Saturn is perhaps the most beautiful of all the planets, famous for its stunning ring system. Even through a small telescope, Saturn's rings are visible, and they're breathtaking. The rings are made of countless particles of ice and rock, ranging in size from grains of sand to house-sized boulders, all orbiting Saturn in a vast flat disk. The rings are wide, over 170,000 miles from inner edge to outer edge, but they're remarkably thin, in most places only about 30 feet thick. If you built a scale model of Saturn's rings where they were 1,000 feet across, they'd be thinner than a razor blade. Despite their thinness, the rings contain a lot of material, enough to build a moon several hundred miles across. But that material is spread out in a vast flat sheet rather than clumped together. We're not entirely sure how Saturn's rings formed. They might be the remnants of a moon that was torn apart by tidal forces when it ventured too close to Saturn. They might be leftover material from Saturn's formation that never coalesced into moons. What we do know is that the rings are surprisingly young, possibly only 100 million years old or so. This is recent in geological terms, meaning that for most of Saturn's history, it didn't have rings, and the rings won't last forever either. The ice particles are gradually spiraling inward, raining down onto Saturn, and within 100 million years or so, the rings might be gone entirely. We happen to be living at just the right time to see Saturn with rings. If intelligent life had evolved on Earth 100 million years earlier or 100 million years later, they would have looked at Saturn through telescopes and seen a ringless planet. Beautiful, perhaps, but missing that spectacular feature that makes Saturn so iconic. Saturn itself is a gas giant similar to Jupiter, but smaller and less massive. It has a diameter of about 74,000 miles, almost 10 times Earth's diameter, but it's much less dense than Jupiter. In fact, Saturn is the least dense planet in the solar system. Its density is less than water, which means that if you could find an ocean large enough to put Saturn in, it would float. Of course, such an ocean doesn't exist, and Saturn's enormous gravity would disrupt anything nearby. But it's a fun thought experiment that illustrates just how light and puffy Saturn is. Like Jupiter, Saturn is made mostly of hydrogen and helium, with a rocky core buried deep beneath thousands of miles of atmosphere and liquid hydrogen. Saturn takes about 29.5 Earth years to orbit the Sun, so seasons on Saturn last about 7 years each. As Saturn orbits, the angle at which we see the rings changes. Sometimes we see them nearly edge-on, and they almost disappear from view because they're so thin. Other times we see them tilted, and they're spectacular. This changes Saturn's appearance dramatically over the decades. When the rings are edge-on, Saturn looks much dimmer because we're not seeing the sunlight reflected off the rings. When the rings are fully open, Saturn brightens considerably and becomes one of the most striking objects in the night sky. Ancient astronomers didn't have telescopes powerful enough to see the rings clearly, and some early observers thought Saturn had ears or handles. It wasn't until Christian Huygens in 1655 correctly identified them as ring system surrounding the planet. Saturn has at least 146 known moons, more than any other planet in the solar system, though Jupiter might catch up as we discover more small moons around both planets. The largest of Saturn's moons is Titan, and it's one of the most fascinating objects in the entire solar system. Titan is the only moon with a thick atmosphere, thicker even than Earth's. The atmospheric pressure at Titan's surface is about 1.5 times Earth's surface pressure. But Titan's atmosphere is mostly nitrogen with some methane, and the temperature is minus 290 degrees Fahrenheit. At these temperatures, water ice is as hard as rock, and methane exists as a liquid. Titan has lakes and rivers and rain, but they're not made of water. They're made of liquid methane and ethane. Titan is the only other body in the solar system besides Earth with stable liquid on its surface. The Cassini spacecraft, which orbited Saturn from 2004 to 2017, mapped Titan's surface using radar that could penetrate the thick, hazy atmosphere. What it found was a world that looks remarkably Earth-like in some ways. There are river valleys carved by flowing liquid. There are lakes and seas, particularly near the poles. The largest, Kraken Mare, is bigger than the Caspian Sea on Earth. There are mountains made of water ice and plains covered in organic sand dunes. The organic material that rains out of Titan's atmosphere accumulates on the surface, forming sediments that wind shapes into dunes hundreds of feet tall. It's a landscape that would be familiar in its broad features, hills and valleys and shorelines, but utterly alien in its details. With rivers of methane flowing through ice mountains under an orange sky. The Huygens probe, part of the Cassini mission, landed on Titan in 2005, giving us our only glimpse of the surface from ground level. The images it sent back showed a landscape of rounded ice boulders scattered across a plain with what looked like channels or gullies indicating liquid flow. The ice boulders had a weathered appearance, smoothed by eons of methane rain. It looked cold and alien, but also strangely beautiful. A world where the chemistry of life as we know it couldn't function because everything is too cold. But where complex organic chemistry is happening everywhere. Some scientists speculate that Titan might have a different kind of life, one based on liquid methane instead of liquid water, using different chemistry, but still recognizably alive. It's speculative, but Titan is exactly the kind of place where we should keep an open mind. Another of Saturn's moons, Enceladus, is even more intriguing for the search for life. Enceladus is small, only about 300 miles in diameter, but it has a remarkable feature, active ice geysers at its south pole. These geysers shoot plumes of water ice and vapor out into space, some of it falling back to the surface as snow, some of it escaping to form one of Saturn's faint outer rings. The Cassini spacecraft flew through these plumes multiple times, analyzing their composition. The water contains salt and organic molecules, and there are small silica particles that probably come from hydrothermal vents on the ocean floor. This all points to the same conclusion. Beneath Enceladus's icy crust, there's a global ocean of liquid water, and that ocean is in contact with a rocky core where hydrothermal chemistry is happening. It's the same kind of environment where life might have started on Earth. In the warm water around hydrothermal vents, protected from the harsh conditions on the surface. Enceladus is shooting samples of its ocean into space, and we've already flown through and analyzed them. We know what's in Enceladus's ocean without even having to land. Future missions could return to Enceladus with more sophisticated instruments specifically designed to look for biosignatures, chemical signs of life. We could potentially discover extraterrestrial life without ever having to drill through miles of ice or build submarines. We just need to fly through the geysers with the right instruments. It's one of the most accessible places in the solar system to search for life beyond Earth. We're 40 facts in, nearly halfway through our journey. The outer solar system is a cold and distant place, but it's full of surprises and wonders. Take a slow breath. Feel yourself drifting like a spacecraft through these distant realms. Uranus is the 7th planet from the Sun, orbiting at a distance of about 1.8 billion miles, nearly 20 times farther from the Sun than Earth. At that distance, sunlight is incredibly faint, and the Sun appears as just a bright star rather than the brilliant disk we see from Earth. Uranus takes 84 Earth years to complete one orbit, so each season on Uranus lasts about 21 years. But Uranus's seasons are stranger than any other planet's because of its extreme axial tilt. Most planets rotate roughly upright relative to their orbital plane. Earth is tilted 23.5 degrees, which gives us our seasons. But Uranus is tilted 98 degrees. It's essentially rotating on its side, rolling around the Sun like a barrel rather than spinning like a top. This extreme tilt means that Uranus's seasons are bizarre. For about 21 years, one pole points almost directly at the Sun, experiencing continuous daylight, while the other pole experiences continuous darkness. Then, as Uranus moves around its orbit, the Sun appears to move toward the equator, and both poles experience day and night cycles. Then the other pole has its turn in the Sun for 21 years, while the first pole is plunged into darkness. If you lived on Uranus's poles, you'd experience a day that lasted 42 years, followed by a night that lasted 42 years. Your entire lifetime might pass in one long day or one long night. We don't know for certain what caused Uranus's extreme tilt. The leading theory is that early in the solar system's history, Uranus was hit by an Earth-sized object in a massive collision. The impact knocked Uranus onto its side, and it's been rolling around the Sun ever since. This same collision might have created some of Uranus's moons from the debris. It's another reminder of how violent the early solar system was, with planets and protoplanets crashing into each other, reshaping worlds in cataclysmic impacts. Uranus is an ice giant, different from the gas giants Jupiter and Saturn. While gas giants are mostly hydrogen and helium, ice giants like Uranus have a larger proportion of water, methane, and ammonia, which astronomers call ices, even though they're not frozen at the temperatures and pressures inside these planets. Uranus has a small rocky core surrounded by a mantle of these ices in liquid or slushy form, and then a thick atmosphere of hydrogen, helium, and methane. The methane in the atmosphere is what gives Uranus its distinctive blue-green color. Methane absorbs red light and reflects blue and green, so Uranus appears as a pale, featureless blue-green disk when viewed through telescopes. Uranus is the only planet visited by just one spacecraft. Voyager 2, which flew past in 1986, Voyager 2 discovered 10 new moons and 2 new rings, measured Uranus's magnetic field, and gave us our only close-up images of the planet and its moons. What those images showed was a surprisingly bland planet with very few visible features in its atmosphere. Unlike Jupiter and Saturn with their complex bands and storms, Uranus looked like a smooth blue-green ball with hardly any variation. This was probably because Voyager 2 arrived during Uranus's equinox when the Sun was shining on the equator. Since then, as Uranus has moved in its orbit and the Sun has moved toward one of the poles, ground-based telescopes have observed increasing atmospheric activity, with storms and bands becoming visible. Uranus is less boring than it first appeared. We just happened to see it during its quietest season. Uranus has a ring system, though it's much fainter than Saturn's. The rings were discovered in 1977 when astronomers observed Uranus passing in front of a star. They expected the star's light to dim briefly as Uranus blocked it, but before and after the planet passed in front of the star, they detected several brief dips in the star's brightness. These dips were caused by narrow rings around Uranus that hadn't been visible in direct observations. Uranus's rings are made of dark particles, probably rocky material and organic compounds, and they're very narrow, some less than a mile wide. We don't know exactly how they formed, but they're probably the result of moons that were shattered by impacts or tidal forces. Uranus has 27 known moons, all named after characters from the works of William Shakespeare and Alexander Pope, a unique naming convention among solar system moons. The largest five, Miranda, Ariel, Umbriel, Titania, and Oberon, are substantial worlds in their own right. Miranda is particularly interesting because its surface shows evidence of incredible geological activity at some point in the past. There are giant cliffs, some over 3 miles high, and regions where different types of terrain meet at sharp boundaries, as if pieces of different worlds were stitched together. One theory is that Miranda was shattered by an impact and then reassembled from the pieces, with the fragments not quite fitting back together perfectly. It's a moon that looks like it's been through a catastrophe and survived. Neptune is the 8th and outermost planet in our solar system, orbiting at an average distance of about 2.8 billion miles from the Sun. At that distance, Neptune receives less than 1% of the sunlight that Earth does, and the Sun appears about 900 times dimmer than it does from Earth. Neptune takes 165 Earth years to orbit the Sun, so a year on Neptune is longer than a human lifetime. Since its discovery in 1846, Neptune has only completed one full orbit in 2011. If you were born when Neptune was discovered, you'd need to live to be 165 years old to see it return to the same position in its orbit. Neptune was the first planet discovered through mathematical prediction rather than direct observation. By the early 1800s, astronomers had noticed that Uranus wasn't following the orbit predicted by Newton's laws of gravity. It would speed up and slow down in ways that couldn't be explained by the gravitational influence of the known planets. Some astronomers suggested there must be another planet beyond Uranus, and its gravity was perturbing Uranus's orbit. In 1846, French mathematician Urbain Le Verrier calculated where this unknown planet should be based on the irregularities in Uranus's orbit. He sent his calculations to Johann Galle at the Berlin Observatory, and that very night, Galle pointed his telescope to the predicted position and found Neptune less than 1 degree from where Le Verrier said it would be. It was a spectacular triumph for mathematical astronomy and Newtonian physics. Like Uranus, Neptune is an ice giant, with a composition dominated by water, methane, and ammonia ices. But unlike bland Uranus, Neptune is a strikingly beautiful deep blue color, again because of methane in its atmosphere. But Neptune's blue is richer and more vibrant. And unlike Uranus, Neptune has a very active atmosphere with visible storms and clouds. When Voyager 2 flew past Neptune in 1989, it found a dynamic world with the fastest winds in the solar system, reaching speeds of over 1,300 miles per hour. These supersonic winds drive enormous storms across Neptune's face. The most famous was the Great Dark Spot, a storm system similar to Jupiter's Great Red Spot, but only about half the size. The Great Dark Spot was observed by Voyager 2, but when the Hubble Space Telescope looked at Neptune a few years later, the Great Dark Spot had disappeared, replaced by other storms in other parts of the atmosphere. Neptune storms come and go, which is different from Jupiter's Great Red Spot that has persisted for centuries. Neptune has a strong internal heat source. It radiates about 2.6 times as much energy as it receives from the Sun, which is surprising given how far it is from the Sun and how little sunlight it receives. This internal heat drives Neptune's atmospheric dynamics and might explain why Neptune has such active weather despite being so cold and receiving so little solar energy. We're not entirely sure where this heat comes from. It might be leftover heat from Neptune's formation, slowly leaking out over billions of years. Or there might be ongoing chemical processes in Neptune's interior that release energy, perhaps methane and ammonia, separating out and falling toward the core, releasing gravitational potential energy. Neptune has 14 known moons, the largest of which is Triton. Triton is unusual in several ways. First, it orbits Neptune in a retrograde direction, opposite to Neptune's rotation and opposite to the direction most moons orbit their planets. This strongly suggests that Triton didn't form around Neptune, but was captured, probably from the Kuiper Belt, a region of icy bodies beyond Neptune's orbit. Triton is about the same size and composition as Pluto, and it might have had a similar origin before Neptune's gravity captured it. When Triton was captured, its orbit would have been highly elliptical, and tidal forces would have generated enormous heat inside the moon, possibly melting its interior. Over time, tidal interactions circularized Triton's orbit, but those same tidal interactions are now causing Triton to gradually spiral inward toward Neptune. In a few billion years, Triton will either crash into Neptune or be torn apart by tidal forces to form a spectacular ring system. Triton is one of the coldest objects in the solar system, with surface temperatures around minus 390 degrees Fahrenheit. But despite the cold, Triton is geologically active. Voyager 2 discovered active geysers on Triton, plumes of nitrogen gas erupting from beneath the surface and carrying dark organic material that falls back down to create dark streaks on the icy surface. These geysers are driven not by internal heat, but by sunlight. Even at Neptune's distance, sunlight can penetrate Triton's relatively clear ice, heating darker material beneath the surface. This creates pockets of nitrogen gas under pressure, which eventually breaks through the ice in geyser eruptions. It's a form of geological activity driven directly by the sun, a solar-powered cryovolcanism unlike anything else we've seen. 50 facts. And we're moving beyond the realm of planets most people learn about in school. But the universe doesn't end with Neptune. There are dwarf planets, asteroids, comets, and billions of exoplanets around other stars. Rest now if you need to. The cosmos will wait. Pluto was discovered in 1930 by Clyde Tombaugh, a young astronomer at Lowell Observatory in Arizona. For 76 years, Pluto was considered the 9th planet, the smallest and most distant, orbiting the Sun at an average distance of about 3.7 billion miles. Pluto's orbit is strange, very elliptical and tilted compared to the 8 classical planets. At times, Pluto is closer to the Sun than Neptune, though their orbits never actually cross because of the tilt. Pluto takes 248 years to orbit the Sun, and it won't return to where it was when it was discovered until the year 2178. Pluto is tiny, smaller than Earth's moon, with a diameter of about 1,400 miles. It's made mostly of rock and ice, probably with a rocky core and a thick mantle of water ice surrounding it. When it was first discovered, astronomers thought Pluto might be quite large. But as observations improved, Pluto kept getting smaller in their estimates. By the 1970s, it was clear that Pluto was far smaller than any of the classical planets, more comparable to moons than to planets. And in the 1990s, astronomers began discovering other objects in the Kuiper Belt, the region of icy bodies beyond Neptune where Pluto orbits. Some of these objects were almost as large as Pluto. One, discovered in 2005 and later named Eris, appeared to be slightly larger than Pluto. This discovery forced a reckoning. If Pluto was a planet, shouldn't Eris be a planet too? And what about the dozens or hundreds of other large Kuiper Belt objects that might be out there waiting to be discovered? Would we end up with dozens of planets, most of them small, icy worlds in the outer solar system? In 2006, the International Astronomical Union held a contentious meeting and voted to create a new category of objects called dwarf planets. To be a full planet, An object must orbit the Sun, be massive enough for its gravity to make it roughly spherical, and have cleared its orbit of other debris. Pluto meets the first two criteria but not the third. Its orbit crosses Neptune's, and it shares the Kuiper belt with thousands of other objects. So Pluto was reclassified as a dwarf planet, along with Eris and a few others. The decision was controversial and remains so. Many people, especially those who grew up learning that Pluto was a planet, felt a sense of loss. Pluto was beloved, the underdog, the little planet at the edge of the solar system. Some scientists argued that the definition of planet was arbitrary and that Pluto should have been grandfathered in. Others defended the decision, saying that science must adapt as we learn more and that it makes more sense to have 8 planets rather than hundreds. The debate continues, though the official classification stands. Pluto is a dwarf planet, the largest known object in the Kuiper belt, but no longer the 9th planet. In 2015, NASA's New Horizons spacecraft flew past Pluto, giving us our first close-up look at this distant world. What it found was astonishing. Instead of a dead, cratered ice ball, Pluto turned out to be a geologically active world with diverse terrain. There are mountains of water ice reaching over 2 miles high. There are vast plains of frozen nitrogen, smooth and free of craters, indicating the surface has been resurfaced recently in geological terms. There's a giant heart-shaped region called Tombaugh Regio, partly covered in nitrogen ice. There are signs of ice volcanoes that might have erupted slush of water, nitrogen, and ammonia. Pluto has a thin atmosphere of nitrogen methane and carbon monoxide that freezes and falls to the surface when Pluto is farther from the Sun in its orbit, then sublimes back into gas as Pluto approaches the Sun. Pluto has 5 known moons, the largest being Charon, which is about half Pluto's size. Charon is so large relative to Pluto that they're sometimes considered a binary system rather than a planet and moon. The center of mass around which they orbit isn't inside Pluto, but in the space between them. Pluto and Charon are tidally locked to each other, so the same side of Pluto always faces Charon and vice versa. If you were standing on the right spot on Pluto's surface, Charon would hang motionless in the sky, never rising or setting, always in the same position. From the other side of Pluto, you'd never see Charon at all. The surface of Charon is quite different from Pluto's. It's mostly water ice, grayer and more uniform than Pluto's diverse terrain. But Charon has some surprising features, including a dark polar cap that scientists think might be made of organic materials that escaped from Pluto's atmosphere, were captured by Charon's weak gravity, and accumulated at the cold pole. There are also enormous canyons on Charon, some of which are 4 to 6 miles deep, suggesting that Charon's interior froze and expanded, cracking the surface. Beyond Pluto and the Kuiper belt, there's the scattered disk, a region of space containing objects on highly elliptical and tilted orbits, probably kicked out there by gravitational interactions with Neptune. And beyond that is the Oort cloud, a vast spherical shell of icy objects surrounding the entire solar system, at distances of thousands or even tens of thousands of astronomical units. The Oort cloud is thought to contain trillions of comets, frozen chunks of ice and rock left over from the solar system's formation. Occasionally, gravitational perturbations from passing stars or the gravitational tide of the Milky Way galaxy send one of these comets falling inward toward the Sun, where it heats up, develops a coma and tail, and becomes visible from Earth. Every comet we've ever seen came from either the Kuiper belt or the Oort cloud, visitors from the frozen outer reaches of the solar system. The Oort cloud is so distant and so faint that we've never directly observed it. We infer its existence from the comets that come from that direction and from theoretical models of solar system formation. The outer edge of the Oort cloud might extend halfway to the nearest star. It's the farthest extent of the Sun's gravitational influence, the true edge of the solar system. Beyond that is interstellar space, the vast gulf between stars. Now we're moving beyond our own solar system to the planets orbiting other stars, worlds that we call exoplanets. For most of human history, we didn't know for certain that any other stars had planets. We suspected they did. It seemed likely, but we had no proof. That changed in the 1990s. The first confirmed detection of an exoplanet orbiting a sun-like star came in 1995. Swiss astronomers Michel Mayer and Didier Queloz announced they had found a planet orbiting the star 51 Pegasi, about 50 light-years from Earth. The planet, now called 51 Pegasi b, or informally Dimidium, was unlike anything in our solar system. It was about half the mass of Jupiter, a gas giant, but it orbited its star once every 4 days. That means it was incredibly close to its star, much closer than Mercury is to our Sun, orbiting in a tight, fast loop. Astronomers called these hot Jupiters gas giants that had somehow migrated inward or formed close to their stars. The discovery of 51 Pegasi b opened the floodgates. Within a few years, dozens of exoplanets were discovered, and within a decade, hundreds. Today, we've confirmed over 5,000 exoplanets, with thousands more candidates waiting to be verified. We've found planets around nearly every type of star. Small red dwarfs, sun-like yellow stars, and massive blue giants all seem to have planets. The galaxy is full of them. We found exoplanets using several different methods. The most successful is the transit method, where we watch for the slight dimming of a star's light as a planet passes in front of it, blocking a tiny fraction of the star's light. NASA's Kepler Space Telescope used this method to discover thousands of planets by continuously monitoring over 100,000 stars for years. Another method is the radial velocity method, which detects the tiny wobble in a star's motion caused by the gravitational pull of an orbiting planet. As the planet orbits, it pulls the star slightly toward it, then away, causing the star's light to be slightly red-shifted and blue-shifted in a regular pattern. By measuring this wobble, we can infer the presence of planets and estimate their masses and orbital periods. 60 facts in, and we've left our solar system behind, venturing into the vast catalog of alien worlds. Let your mind wander among these distant planets. There's no need to hold on to every detail. Just drift. The variety of exoplanets we've discovered is staggering. There are hot Jupiters like 51 Pegasi b, massive gas giants orbiting so close to their stars that their atmospheres are being stripped away by stellar radiation. There are super-Earths, rocky planets larger than Earth but smaller than Neptune, a type of planet that doesn't exist in our solar system. There are many Neptunes, worlds with thick hydrogen atmospheres, but smaller than Neptune itself. There are planets orbiting binary star systems, where two suns rise and set in the sky like in Star Wars. There are rogue planets, worlds that don't orbit any star at all but drift through interstellar space alone. There are planets orbiting pulsars, the rapidly spinning corpses of exploded stars bombarded by intense radiation. The universe has been more creative with planets than we ever imagined. One of the strangest exoplanets discovered is called HD 189733b. It's a hot Jupiter, orbiting a star about 63 light-years away. Observations suggest that the atmosphere of this planet contains silicate particles, essentially tiny grains of glass. Wind speeds in the atmosphere reach over 5,000 miles per hour, which means this planet likely has sideways glass rain driven by supersonic winds. The planet would appear deep blue if we could see it, not because of the water like Earth, but because of the way light scatters off those silicate particles in the atmosphere. It's a beautiful blue world where it rains molten glass in howling supersonic winds. Another remarkable exoplanet is Kepler 16b, which orbits two stars. It's a real-life Tatooine, the desert planet from Star Wars with two suns in the sky. From the surface of Kepler 16b, you'd see two suns, one larger and brighter, one smaller and dimmer, both moving across the sky, sometimes close together, sometimes separated, creating complex lighting conditions throughout the day. Kepler 16b is a cold gas giant, probably not habitable, but it proves that planets can form and remain stable in binary star systems. This dramatically increases the number of potential planetary systems in the galaxy. Since about half of all stars are in binary or multiple star systems, some exoplanets orbit in the habitable zones of their stars. the regions where temperatures might allow liquid water to exist on a rocky surface. These are the worlds that most excite astrobiologists because liquid water is essential for life as we know it. One such planet is Proxima Centauri b, orbiting the closest star to our Sun, just 4.2 light-years away. Proxima Centauri is a red dwarf star, much smaller and cooler than our Sun, so its habitable zone is much closer in. Proxima b orbits once every 11 days at a distance where it might have liquid water, making it possibly the closest potentially habitable world to Earth. But Proxima Centauri is an active star, prone to powerful flares that could strip away any atmosphere Proxima b might have had. Whether the planet is actually habitable is still an open question. The TRAPPIST-1 system, about 40 light-years away, contains 7 Earth-sized planets, 3 of which orbit in the habitable zone. This system is remarkable because it's packed with planets all orbiting very close to their star, a cool red dwarf. The innermost planet orbits in just 1.5 days, and even the outermost planet orbits in only 20 days. All 7 planets are probably rocky like Earth, and they're close enough together that if you were standing on one, you'd see the others in the sky, appearing larger than the Moon does from Earth. Some might show phases like Venus does from Earth. It would be a spectacular sky, and it's tantalizing to imagine that one or more of these worlds might harbor life. If life exists on multiple planets in the same system, could it have spread from one planet to another via asteroid impacts, seeding life across the system? It's speculative, but TRAPPIST-1 is exactly the kind of system where such ideas could be tested. We've also discovered water vapor in the atmospheres of some exoplanets. Using spectroscopy, astronomers can analyze the starlight that passes through a planet's atmosphere during a transit, and the way different wavelengths are absorbed tells us what gases are present. We've found water vapor, methane, carbon dioxide, and other molecules in the atmospheres of various exoplanets. Recently, the James Webb Space Telescope has begun studying exoplanet atmospheres in unprecedented detail, looking for biosignatures, chemicals that might indicate biological activity. Finding oxygen or methane or other gases in certain combinations in a rocky planet's atmosphere could potentially indicate life, though we'd need to be very careful to rule out non-biological processes that could produce the same signatures. Some planets are so different from anything in our solar system that they challenge our understanding of how planets form and evolve. There are planets with densities so low they must be incredibly puffy, expanded by intense heat from their nearby stars. There are planets so massive they blur the line between planet and brown dwarf, failed stars that aren't quite massive enough to sustain hydrogen fusion. There are planets with such eccentric orbits that they swing from scorching heat to freezing cold and back again. There are planets tidally locked to their stars, with one side in perpetual daylight and the other in eternal night, possibly with a narrow twilight band where conditions might be temperate enough for life. One of the goals of exoplanet research is to find Earth 2.0, a rocky planet about Earth size, orbiting in the habitable zone of a sun-like star. We haven't found an exact match yet, but we've found several candidates. These are worlds where, if we could somehow visit them, we might find oceans and continents, atmospheres we could potentially breathe with the right equipment, climates that range from poles to equator. We might find life, perhaps microbial, perhaps complex, perhaps even intelligent. Or we might find sterile worlds where life never arose, teaching us how rare or common the spark of life truly is. The discovery of exoplanets has fundamentally changed how we think about our place in the universe. We now know that planets are common, probably outnumbering stars. Most stars have planets. That means there are hundreds of billions of planets just in our galaxy alone, and there are hundreds of billions of galaxies. The number of planets in the universe is almost incomprehensibly large. Among all those planets, surely some have conditions similar to Earth. Surely some have liquid water, stable climates, protection from radiation. And if the conditions are right on enough planets, surely life has arisen elsewhere. The question isn't whether other life exists, but how common it is, how far away the nearest living world is, and whether any of that life has developed intelligence and technology. 70 facts. And we're deep into the realm of worlds we've never seen. Worlds we can only infer from the wobbles of distant stars and the dimming of their light. But what we've learned is profound. We're not alone in having planets. The universe is full of worlds. Some planets might have life that's completely different from anything on Earth. Life on Earth is carbon-based, uses water as a solvent, and operates within a relatively narrow temperature range. But there's no law of physics that says life must follow these rules. On a cold world like Titan, life might use liquid methane instead of water and have a completely different biochemistry. On a hot world with a thick atmosphere, life might float in the clouds, never touching the surface. On a world with high radiation, life might evolve incredible DNA repair mechanisms or use different genetic molecules altogether. The possibilities are endless, and we've only just begun to think about them systematically. Some exoplanets are so close to Earth that future telescopes might be able to directly image them, to actually see the planet as a separate point of light from its star, rather than just inferring its existence. These direct images would be incredibly valuable. By analyzing the light reflected off the planet, we could determine its color, look for seasonal changes as it orbits, detect weather patterns, and even potentially see surface features if the images are good enough. We could watch exoplanets change over time, seeing storms come and go, ice caps expand and contract, oceans reflecting light differently than continents. We'd be studying alien meteorology and alien geography from light years away. The James Webb Space Telescope, launched in late 2021, is beginning to revolutionize exoplanet science. Its infrared sensitivity allows it to study the atmospheres of exoplanets in detail, detecting molecules that previous telescopes couldn't see. Future telescopes, both ground-based and space-based, will be even more capable. There are plans for telescopes that could directly image Earth-sized planets in the habitable zones of nearby stars, telescopes that could analyze their atmospheres for signs of life, telescopes that might even detect city lights on the night sides of planets or industrial pollution in their atmospheres. Within our lifetimes, we might answer the age-old question, are we alone? The Drake equation is a famous formula proposed by astronomer Frank Drake in 1961 to estimate the number of active, communicative, extraterrestrial civilizations in our galaxy. It multiplies together several factors: the rate of star formation, the fraction of stars with planets, the number of planets per star that might support life, the fraction where life actually arises, the fraction where intelligent life develops, the fraction that develop technology and try to communicate, and how long such civilizations last. When Drake first proposed it, we could only guess at most of these numbers. Now, thanks to exoplanet discoveries, we can actually constrain some of them. We know most stars have planets. We know rocky planets in habitable zones are fairly common, but we still don't know how commonly life arises, how often it becomes intelligent, or how long civilizations last. Those remain the great unknowns. The Fermi paradox asks, if intelligent life is common in the universe, where is everybody? If there are billions of potentially habitable planets in our galaxy, and if life and intelligence are natural outcomes given the right conditions, then surely some civilizations should be millions or billions of years older than us. They should have spread across the galaxy. We should see evidence of them everywhere. Yet we don't. We see no signs of galactic civilizations, no megastructures, no clearly artificial signals. The galaxy seems silent. Why? There are many proposed solutions to the Fermi paradox. Maybe intelligent life is incredibly rare, and we're among the first. Maybe civilizations destroy themselves shortly after developing technology, so they don't last long enough to spread. Maybe interstellar travel is harder than we think, and civilizations stay confined to their home systems. Maybe advanced civilizations deliberately hide themselves, not wanting to be found. Maybe they're out there but communicating in ways we haven't thought to listen for. Maybe the galaxy is full of life, but mostly at a microbial level, and intelligence is the rare thing. Or maybe they're already here observing us and we just haven't recognized them. Each solution has implications for our future and for the nature of life in the universe. The concept of planetary habitability has evolved as we've learned more. We used to think the habitable zone was a narrow band around a star where liquid water could exist. Now we realize habitability is more complex. A planet needs not just the right temperature, but also the right atmospheric pressure, protection from radiation, geological activity to recycle nutrients, a stable orbit, and probably a large moon to stabilize its axial tilt. It might need plate tectonics. It might need a magnetic field. The list of requirements keeps growing, which could mean habitable planets are rarer than we thought, or it could mean life is more adaptable than we thought, and these requirements aren't all necessary. Moons of exoplanets, which we call exomoons, might also be habitable. In our solar system, several moons have conditions that might support life. The same could be true elsewhere. A large moon orbiting a gas giant in the habitable zone might have liquid water, an atmosphere, and active geology. It might be even more habitable than a planet in some ways. And a moon of a gas giant could have a much more stable orbit than a small planet, protected by its massive parent from asteroid impacts and orbital perturbations. Detecting exomoons is incredibly difficult with current technology, but there are hints that some of the exoplanets we found might have large moons. As our instruments improve, we'll start finding and studying these worlds within worlds. Rogue planets, worlds that don't orbit any star, are another fascinating category. These planets were probably ejected from their home star systems through gravitational interactions with other planets. They drift through interstellar space, dark and cold, lit only by the faint glow of distant stars. There might be billions of rogue planets in our galaxy, outnumbering planets that orbit stars. Some of these rogue planets might even be habitable, not on their surfaces, but beneath them. A large rogue planet could have enough internal heat from radioactive decay to maintain a liquid water ocean beneath a thick ice crust, similar to Jupiter's moon Europa. Life could potentially exist in these underground oceans, completely independent of any star, thriving in eternal darkness on a world that drifts alone through the void. Some stars are orbited by debris disks, vast clouds of dust and gas left over from planet formation or created by collisions between asteroids and comets. Our solar system has several of these debris structures, including the asteroid belt and the Kuiper belt. When we observe similar structures around other stars, they tell us about the architecture of those planetary systems. Gaps in the debris disks might indicate the presence of planets clearing out their orbits. Clumps of material might be shepherded by the gravity of unseen planets. These indirect signatures allow us to infer planetary systems even when we can't detect the planets directly. 80 facts, and we're floating through a universe teeming with worlds. Each one is a potential story, a potential home for life, a place where chemistry becomes biology, where rocks and water and sunlight conspire to create something living. Rest your mind among these infinite possibilities. The study of exoplanet atmospheres has revealed some truly bizarre weather patterns. On HD 1899733b, the hot Jupiter with glass rain, the temperature difference between the day side and the night side creates winds that transport heat around the planet. On some hot Jupiters, we've detected clouds made of vaporized minerals that would be solid rock on Earth, but exist as gas in these scorching atmospheres. Some planets might have rain made of iron, or droplets of liquid rock falling through atmospheres thick with metallic vapors. The weather on these worlds would be deadly and spectacular, storms unlike anything Earth has ever experienced. The concept of a habitable zone varies depending on the type of star. Around a massive hot star, the habitable zone is far from the star and quite wide. But massive stars burn through their fuel quickly, lasting only millions of years rather than billions. There might not be enough time for complex life to evolve on planets in these systems. Around small, cool, red dwarf stars, the habitable zone is very close to the star and quite narrow. Planets there would probably be tidally locked, always showing the same face to their star. The day side would be scorching, the night side freezing, with potentially a narrow band in between where temperatures might be right for liquid water. Red dwarfs also tend to be very active, emitting powerful flares that could strip away planetary atmospheres. But red dwarfs are the most common type of star, and they live for trillions of years. So if life can survive on planets around red dwarfs, these systems might ultimately host the most life in the galaxy. There's a concept called panspermia, the idea that life could spread from one planet to another, or even from one star system to another, carried on asteroids or comets. In our solar system, rocks have been knocked off the surface of Mars by asteroid impacts and later fell to Earth as meteorites. If there was ever life on Mars, could it have hitched a ride on one of these rocks and survived the journey to Earth? Could life on Earth have originated on Mars and been transported here? Some extremophile bacteria can survive in space for extended periods, enduring radiation, vacuum, and extreme temperatures. If life can survive interplanetary transfer within a star system, might it also survive interstellar transfer given enough time? Could life have originated once in the galaxy and then spread from system to system over billions of years? It's a fascinating idea, though proving it would be incredibly difficult. The sheer number of exoplanets means that, statistically, some very strange configurations must exist. There are probably planets in the process of being torn apart by their stars, with long comet-like tails of evaporating atmosphere streaming behind them. There are probably planets in highly eccentric orbits that bring them very close to their stars at some points and very far away at others, experiencing extreme seasonal variations. There are probably planets orbiting the supermassive black holes at the centers of galaxies if they can survive the intense gravitational forces and radiation. There might be planets made almost entirely of diamond, carbon planets, where the pressure is so high that carbon crystallizes. The universe is vast, and given enough planets, every possible configuration will occur somewhere. One of the most important questions we can ask about exoplanets is whether any of them are currently inhabited, not just capable of supporting life, but actually hosting life right now. Statistically, it seems almost certain that life exists elsewhere in the universe. But where is the nearest living world? Is it in our solar system, perhaps beneath the ice of Europa or Enceladus? Is it orbiting a nearby star just a few light years away? Or is life so rare that the nearest living world is hundreds or thousands of light years distant? The answer to this question will shape humanity's future and our understanding of our place in the cosmos. If we do discover life on another planet, even if it's just bacteria, it would be one of the most profound discoveries in human history. It would tell us that we're not alone, that life is not confined to Earth, that the universe is biologically active. It would raise immediate questions. Did this life arise independently from Earth life, or is it related through panspermia? What is its biochemistry? Does it use DNA? Does it have the same amino acids and sugars as Earth life, or completely different ones? Is it based on the same fundamental principles, or has evolution found entirely different solutions on this other world? And if we were to discover intelligent life, life capable of technology and communication, the implications would be even more staggering. We would no longer be the only conscious beings contemplating the universe. There would be other minds, other civilizations, other perspectives. What would they be like? Would they think like us? Or would their psychology be alien beyond our comprehension? Would they be friendly, or would contact be dangerous? These questions have occupied science fiction for over a century, but they might not remain fiction forever. SETI, the search for extraterrestrial intelligence, has been listening for signals from other civilizations for over 60 years. Radio telescopes scan the sky looking for narrow-band signals or mathematical patterns that couldn't be produced by natural processes. So far, we've detected nothing conclusive. The famous WOW signal, detected in 1977, was a strong narrow-band radio signal that lasted 72 seconds and was never detected again. It remains unexplained, possibly from an alien transmission, possibly from some unknown natural phenomenon, or even terrestrial interference. We simply don't know. The search continues, and with better telescopes and more computing power to analyze the data, we're covering more of the sky at more frequencies than ever before. But maybe we're looking for the wrong thing. Advanced civilizations might not use radio waves for communication. They might use lasers, gravitational waves, or technologies we haven't even imagined yet. They might communicate through modulations in neutrino beams or quantum entanglement. They might not broadcast at all, using tightly focused beams for point-to-point communication rather than spraying signals across the galaxy. Or they might have moved beyond physical communication entirely, uploading their consciousnesses into computers or existing in forms we wouldn't recognize as alive. The assumption that aliens would communicate in ways we can detect is itself a very human assumption. There's also the question of whether we should be trying to contact alien civilizations actively. METI, messaging extraterrestrial intelligence, involves deliberately transmitting signals to other star systems in hopes of getting a response. Some scientists think this is a bad idea. They argue that we don't know how an alien civilization would react to discovering us. They might be friendly, or they might see us as a threat or a resource to be exploited. Stephen Hawking warned that contacting aliens could be like Native Americans encountering Columbus. It didn't end well for the natives. Others argue that any civilization capable of reaching Earth would already know we're here, and that trying to hide is futile. Besides, we've been leaking radio and television signals into space for over a century. Any nearby civilization with sensitive enough equipment could already detect us. 90 facts now, and we've explored planets from our backyard to across the galaxy. We've thought about the possibility of other minds, other worlds, where beings might be looking up at their own night skies and wondering if they're alone. Take a deep breath. Feel the comfort of your bed, the weight of your blanket. You're safe here, on this planet, in this moment. The ultimate fate of planets depends on the life cycle of their stars. Our sun is about halfway through its main sequence lifetime. In about 5 billion years, it will exhaust the hydrogen in its core and begin fusing helium. The sun will swell into a red giant, its outer layers expanding past the orbit of Mercury, possibly past Venus, maybe even reaching Earth. The inner planets will either be swallowed or scorched to lifeless cinders. But this won't happen for billions of years, an incomprehensibly long time. Humanity might be long gone by then, or we might have spread to other star systems, or evolved into something unrecognizable. For planets around more massive stars, the end comes much sooner. When these stars exhaust their fuel, they explode as supernovae, obliterating any planets in the system. But these explosions also create and scatter the heavy elements necessary for rocky planets and life. The iron in your blood, the calcium in your bones, the oxygen you breathe, all of it was forged in the cores of massive stars and scattered across the galaxy when those stars exploded. We are literally made of stardust, of the remnants of dead stars. Every atom in your body except for hydrogen was created in stellar nucleosynthesis or supernova explosions. In a very real sense, we are the universe becoming aware of itself. Star matter that evolved consciousness and began asking questions about its own origins. Planets around white dwarfs. The slowly cooling cores left behind when sun-like stars die might persist for trillions of years after their star's death. These planets orbit dead stars in cold, dark systems lit only by the faint glow of the white dwarf. As the white dwarf cools, any remaining planets freeze solid. But white dwarfs cool very slowly, taking trillions of years to radiate away their heat. In the far future, when all the stars have burned out and the universe has grown cold and dark, white dwarfs and their planets might be among the last warm places in the cosmos. There's a concept called a Dyson sphere, proposed by physicist Freeman Dyson. A sufficiently advanced civilization might build a massive structure around its star to capture all of its energy output. This could be a solid shell, though that's probably impossible to engineer, or more likely a swarm of solar collectors orbiting the star. From a distance, such a structure would make the star appear dimmer in visible light, but would glow brightly in infrared as the collected energy is eventually radiated as heat. Astronomers have looked for stars with these unusual signatures, stars that are dimmer than they should be and bright in infrared, as potential signs of alien megastructures. We've found a few candidates, but in every case so far, there's been a more mundane explanation, usually dust or unusual stellar properties. Terraforming is the theoretical process of transforming a planet to make it habitable for humans. Mars is the most commonly discussed target for terraforming. The basic idea would be to thicken Mars's atmosphere, warm the planet, and melt its water ice to create oceans and rainfall. This might be accomplished by releasing greenhouse gases to trap heat, by using orbital mirrors to focus more sunlight on the surface, or by deliberately crashing comets into Mars to add water and volatiles to the atmosphere. It would take centuries or millennia and require technology we don't yet have, but it's theoretically possible. The result would be a second Earth, a warm, wet Mars with blue skies and green landscapes. But terraforming raises ethical questions. Do we have the right to transform another world, possibly destroying any native life that might exist there in the process? Is it hubris to reshape entire planets to suit our needs? These are questions we'll need to answer if we ever develop the capability to terraform. Venus has also been proposed as a candidate for terraforming, though it would be even more challenging than Mars. The extreme heat and crushing atmospheric pressure make Venus seem impossible to transform. But some scientists have proposed creative solutions. One idea is to use genetically engineered bacteria that could live in Venus's upper atmosphere, converting carbon dioxide to oxygen and other compounds, gradually altering the atmospheric chemistry. Over millions of years, this could cool the planet and reduce the atmospheric pressure. Another idea is to build floating cities in Venus's upper atmosphere, where the temperature and pressure are Earth-like. The cities would float on balloons filled with breathable air, which is actually a lifting gas in Venus's thick carbon dioxide atmosphere. People could live comfortably in these cloud cities without ever touching the hellish surface below. Some exoplanets might be artificial, not in the sense of being built from scratch, but in the sense of being deliberately moved or modified. An advanced civilization might move their planet to a safer orbit, farther from their star as it ages and brightens, or they might surround their planet with a shell to protect it from cosmic threats. They might build artificial rings or moons. They might reshape continents or create new oceans. On such worlds, the distinction between natural and artificial would blur. The planet itself would be a work of engineering, a garden tended over millions of years. The concept of a planet as a closed ecosystem is important for understanding habitability and for thinking about long-term space colonization. Earth is essentially a closed system for matter, though not for energy. Atoms cycle through various forms: air, water, rock, living things, but they rarely leave the planet. The energy from the sun drives all the cycles, but the matter itself is reused endlessly. Understanding these cycles, how carbon moves through the atmosphere, oceans and biosphere, how nitrogen is fixed and recycled, how water evaporates and falls as rain, is crucial for understanding what makes Earth habitable. And it's crucial for designing closed-loop life support systems for spacecraft and space colonies. If we're going to live in space or on other planets, we need to recreate these cycles artificially, growing food, recycling air and water, and managing waste in closed systems that can sustain human life indefinitely. The diversity of planets tells us that the universe is far stranger and more varied than we once imagined. Each new discovery challenges our assumptions. Before we found hot Jupiters, we didn't think gas giants could exist so close to their stars. Before we found super-Earths, we didn't have a category for planets larger than Earth but smaller than Neptune. The universe keeps surprising us, and there's no reason to think the surprises will stop. Future telescopes will find even stranger worlds, planets with properties we haven't predicted, orbiting in configurations we haven't imagined. Each discovery expands our understanding of what's possible, of the full range of planetary types and behaviors nature can produce. 100 facts, and our journey through the planets comes to a close. But the universe's planets don't end. There are countless worlds out there, more planets than stars, more stars than grains of sand on all Earth's beaches. Each planet is a world, a place with its own geography, its own weather, its own story, stretching back billions of years. Some are dead and barren, scorched by their stars or frozen in eternal darkness. Others might be teeming with life, with creatures swimming in oceans or flying through skies, with ecosystems as complex and beautiful as Earth's. And maybe somewhere among all those worlds, there are beings like us, conscious and curious, looking up at their night sky and wondering if they're alone, wondering if anyone else is out there looking back, here on Earth. We spin through space on a rocky planet heated by a medium-sized star, one of billions in a galaxy that's one of billions in the observable universe. We're unimaginably small in the cosmic scheme, and yet we're also part of something vast and connected. The atoms in our bodies were forged in stars. The water we drink is as old as the solar system. The oxygen we breathe was produced by microorganisms and plants over billions of years. We're connected to everything, to the planets, to the stars, to the fundamental processes that began with the Big Bang and have been unfolding for nearly 14 billion years. The study of planets, both in our solar system and beyond, is ultimately the study of worlds and the study of possibilities. Each planet represents a different outcome of the same fundamental processes: gravity, chemistry, thermodynamics. Each one shows us a different way matter and energy can organize themselves, a different path cosmic evolution can take. By studying planets, we're learning the rules of the game, the constraints and possibilities that govern how worlds form and evolve. We're learning where life might arise and how common or rare it might be. We're learning about our own planet and what makes it special. What delicate balance of factors came together to create a world where life could not only begin but flourish and eventually become conscious. And in studying planets around other stars, we're preparing for a future when humanity might visit them. It's a distant future, certainly. The nearest star is over 4 light-years away, and with our current technology, it would take tens of thousands of years to reach it. But technology advances. What seems impossible today might be routine in a few centuries. Our descendants might look back at our time and marvel that we were confined to a single planet, unable to reach even the nearest stars, just as we look back at the age before flight and marvel that our ancestors were confined to the surface of the Earth. Maybe someday humans or our descendants or our AI creations will walk on the surface of an exoplanet. We'll breathe air that wasn't made on Earth. We'll look up at an alien sky and see unfamiliar constellations and a sun that isn't ours. They'll be the first to set foot on a new world, the first to explore landscapes that have existed for billions of years without any conscious being to see them. They'll find mountains and valleys, rivers and seas, or strange landscapes we can't imagine because we've never seen anything like them. And maybe they'll find life, beings that evolved completely independently, the product of a different genesis on a different world. Meeting them, understanding them, learning their biology and their world would be the greatest scientific and philosophical achievement in human history. But that's for the future. Tonight now, we're here on Earth, lying in bed thinking about distant worlds, and that's beautiful too. The fact that we can imagine these places, that we can study them from light years away, that we can lie here in the dark and let our minds wander among the planets, is itself something remarkable. Consciousness is strange. Matter organizing itself into patterns complex enough to think, to wonder, to dream. You are a piece of the universe that has become aware of itself, and you're using that awareness to contemplate other pieces of the universe, other worlds spinning through the dark. Rest now. Let go of these thoughts if you need to. The planets will still be there tomorrow, orbiting their stars in the grand cosmic dance that began billions of years ago and will continue for billions more. You've traveled far tonight, from the scorching surface of Venus to the frozen moons of Saturn, from the deserts of Mars to the glass rain of HD 189733b. You've imagined worlds you'll never see and life you'll never meet. And now it's time to come home, to sink into sleep, to let your consciousness dim like a distant star disappearing below the horizon. The universe is vast and strange and full of wonders. But so are you. You're made of stardust, animated by chemical reactions, aware of your own existence, capable of understanding your connection to everything else. That's as miraculous as any planet, as wondrous as any discovery. You're part of this cosmic story, this unfolding of matter and energy across space and time. And right now, your part in that story is simple: to rest, to sleep, to let your body and mind recover for tomorrow's adventures. The planets will wait. The stars will wait. The whole universe will wait while you sleep, spinning on in its patient, eternal rhythms. And when you wake, it will all still be there, still mysterious, still beautiful, still calling to you to explore and wonder and ask questions that reach toward the infinite. Sleep well, traveler among worlds. Dream of distant planets, of alien skies, of the endless frontier waiting among the stars. May your rest be as deep as the void between galaxies and as peaceful as a perfect planet in a perfect orbit around its star. Thank you for journeying with me tonight through these 100 planetary facts. The cosmos is yours to explore in waking and in dreams. Good night.